So we're going to start the assemblies with accessible assemblies. So that's basically stuff that you might have seen a variation of somewhere, to just try to not just jump into a bunch of random machine stuff which you haven't ever seen. So here we have a gate wheel. There's a gate with a wheel, there are wheels on the gate, there's a wheel on the gate. So gate wheels are things that we have everywhere around us in our everyday life. So what I have over here, this is typically the format that an assembly question will be asked in. We will give you the orthographic detailed drawings of a number of parts, and then you need to figure out how to fit them or put them together, either based on the description of the parts or maybe some schematic drawing if it's not a very sensible kind of assembly. For example, wheels on a car always go on the lower side of the car. It just makes sense that way. So then I won't give you a picture to show that the wheels go on the bottom side. But if it's something a little bit more random, then we'll try to kind of hint towards the application. Right, so basically what we can do is we can now look at these individual detailed drawings. There we have a detailed drawing of a big block, 100 high, 100 deep, 140 long. It's got a groove in the top, 40 deep, 50 wide. And it's got these 4 M10 threaded holes that go all the way through. And they are spaced 60 apart in this direction and 100 apart in that direction. M10 means it's a metric screw thread with a nominal diameter of 10 millimeters. Okay, so if you wanted to, you could go and just try and imagine more or less what the parts would look like. Okay, you don't have to make an isometric drawing of each thing, that will just be a waste of your time, but try to visualize more or less how this thing looks like. So that's the first block. At the bottom left here we have 3 views, orthographic views of an L-shaped component. It's got 1 hole in the vertical side and 2 in the horizontal side. It's 50 by 50, and the side there is 15 thick, 50 minus 35. And this bottom side is also 15 thick, 50 minus 35. So something more or less like that. Again, don't draw the isometrics every time. I'm just drawing it so that you can, from your computer side or devices side, just have an idea what it looks like. The one to the right of that, 3 views of a component. It's basically the same as this first one, 100 long, 2 holes, 60 apart, diameter 11. 60, we've seen 60 somewhere before. Okay. This one, however, has a slot here in the front face, in the vertical face. So something like that. Okay, so it helps to visualize more or less in 3D what these components look like. Then what we can do is we can start matching up these dimensions. So over there we've got a wheel. I forgot about the wheel. It has a diameter of 100, hole on the inside of 10, width of 39 and it's got this weird V shape to it. There we have a bolt. It's an M10 bolt, metric screw thread with a 10mm nominal or outside diameter, and the head of the bolt is 15 wide. We've seen a 15 wide somewhere. If that circle there has a diameter of 15, then the width from there to there will also be 15. Okay, so we can now, remember I mentioned that the 11 and the M10 could line up and the spacing is 60 and 60. So the distance between that hole and that hole, the distance there is 60. So I can now go and bring that block in underneath that component. Something like that. Remember the thread was a M10. This hole had a diameter of 11. For those of you who like to work with SolidWorks, a cool thing is if you want to know the diameter of a circle, you can just click on it and it shows you the diameter at the bottom of the screen. Okay. We can also put the other one on the other side. Something like that. Okay, good. So now we've figured out that the hole that's 11 and the spacing 60 will fit nicely with those holes. Something like that. Just want to check the question. So now you would typically not be given the quantity of parts in the test. You'll have to look at how many locations you have to fit them in. Standard components are actually not given in the question itself either. So not only won't you know the quantity, you won't even know the standard component. You'll have to reason that out when you do the assembly. But I'm going to show you that in a couple of minutes. Then we said the width of this bolt's head fits nicely into that 15 groove over there, and the M10 thread will go through the 10mm hole. So that bolt can be inserted through the holes like that. So basically what's going to happen is these sides will stop that bolt head from being able to rotate because it keeps that flat plane and the one on the other side stationary, so it holds it in place. So this is almost like a locking device that's built into a part. Okay, I'm just going to pull the bolt out again. Remember now also the bolt was M10 diameter and the wheel had a 10mm hole through the middle. So if I hover the wheel over there, then I can push the bolt all the way through the wheel, and then it will allow the wheel to spin around the bolt, but the bolt can't spin in this other purple component. You'll see you'll see what I do now. So basically, the bolt gets pushed in all the way by hand. And now when we have a bolt with a little hole in the threaded part. Okay, so a bolt with a hole in the threaded part, like it is shown over there, usually hints towards a castle nut and split pin that is going to be used. So the bolt gets pushed in from the right hand side, and then from the left hand side we can take the castle nut and screw it over the end of the bolt. Okay, so by screwing the castle nut over the bolt, it will actually pull the bolt in the last little bit and keep the bolt tight. Meaning you don't have to be able to turn this bolt because you're going to be pulling it from the other side. If the bolt had to screw into something which was connected to other stuff, then this purple groove there, that groove, will make it impossible for the thing to assemble. Cool, but that was a very good question, and I'm glad you noticed stuff like that. Okay, then castle nut also usually has a split pin somewhere. Okay, so the split pin gets pushed through, and then once it's through the hole, we bend it open on the other side to make sure that it won't fall out by itself. So that split pin will stop the castle nut from coming loose, which means that yellow bolt will never be able to pull out towards the right hand side like I did it now. And this groove will stop the bolt's head from ever being able to spin. So basically, the way I did it now forces this wheel to never be able to turn the bolt. Okay, so the height of the castle nut isn't specifically fixed, so you can just draw it more or less in proportion, then it will be fine. There's no specific rule. Usually the width of the castle nut is the same equation as the width of a bolt, the head of a bolt, so it's 1.5 times the thread diameter. If you do the CAD assignment by hand, no, you don't have to use a ruler. We will never expect you to use rulers. Okay, and now the problem with this assembly still is this block can fall off. So standard components are then used, M10 bolts in this case are used we position them above there, then we screw them down into the threaded component, something like that. So because these standard components weren't given, but we saw that there was a M10 thread with a hole that lined up with it that would be loose without a standard component, then that's how I was supposed to know that I needed to include the standard components. And there we go. Let's quickly check some dimensions. This wheel has a width of 39. This L-shaped component has a width of 50. From the small side to the hole is 20. So from the hole to the inside face is 30. The same for the other one. From the inside face to the hole is 30. Meaning, if I wanted to determine the gap between that blue inside face and this purple plate's inside face, I would need that 100 minus 30 on the one side, that 30 over there, minus 30 on the other side, that 30 over there. So the gap between the two plates, the gap over there, is 100 minus 30 minus 30, so that's 40 millimeters. If I look at the width of the wheel, it's 39. So that means there will be a small gap on the side there, 1 millimeter. So in the exam, the final exam for MGC usually has 30 marks for multiple choice, that's your manufacturing stuff. Then it has around 50 marks or so for an assembly drawing, which basically also automatically includes all of your orthographic stuff like auxiliary views, standard components, section views, dimensioning, all of that. So no, you won't have a detailed drawing and an assembly because an assembly drawing already has most of the drawing skills needed for the detail stuff. So if you can do an assembly, you can do a detail. Yes, next question was, the holes basically direct us to what will be there. Exactly. Yes, very good comment there. The 1 millimeter gap is specifically designed so that the wheel is always slightly loose. If the wheel wasn't loose, then the blue and the purple plates would actually be holding onto the side of the wheel, which will increase the friction and make it harder to turn. That's a very good question as well. When drawing the components, do you split the 1 millimeter gap into two? And there your answer is on the screen. Best practice is actually to draw an equal gap on both sides. Okay, but at the very least, if there is a gap, you must make sure that the gap is shown. There we've got overall dimension, overall dimension, overall dimension. Functional is the wheel diameter and the wheel profile. I need to know that to be able to use this wheel. So this wheel profile will depend on the kind of track that it's going to run on, and that's why it's important to know the profile. And mounting dimensions, this thing, if you wanted to, you could give those 4 holes as mounting dimensions if it maybe gets mounted from the bottom onto some other structure or gate or something. Okay, so in this case we ignored lubrication because it was a very basic assembly, but in the one we're going to do in the class on Wednesday, that one will have lubrication in it as well, I think. No, that one has bearings in it. After that we'll still do lubrication. Okay, so this nut over here is a castle nut. So that's why it's got the 3 sides visible, and the little oval in the middle is the split pin. I did forget to add the threading over there. So typically you'll design the system such that the lateral movement is not a problem. So in this case it would be considered insignificant. What is super interesting though is motor car engines. The big rotating part of a motor car engine called the crankshaft, even that thing has slight axial looseness on the engine. Otherwise, as the engine heats up, the bearings will clamp down on the crankshaft. Typically, they have little thrust bearings called thrust washers, which actually take up the axial forces that your engine has to undergo. For this example, we didn't cut it open, but obviously in other examples, it would be beneficial to make a section view. This was really just as basic as it gets. Okay, let's quickly go to example number 2. So this is a tap or a valve or a stop tap, depending on what kind of tap you're referring to. So these are devices used to regulate or restrict the flow of a fluid. It can be a gas or a liquid. Basically, as you change the cross-sectional area in a small region in the pipe, you can control the fluid flow throughout the whole pipe, because everything has to go through that little hole in any way. So here we have something called a ball valve. This is a rather cheap but very effective tap. Usually only has a 90-degree rotation angle from completely open to completely closed. And basically on the inside it's got a spherical ball with a hole drilled through it. As you rotate the ball, the hole turns up to a point where it's perpendicular to the direction of the fluid flow, which means there's nowhere for the fluid to flow through, and the tap is effectively shut off. This is a cross-sectional drawing or section drawing of a normal tap. So it's got a rotary hand wheel at the top. As you turn the wheel, it's got a thread somewhere, which as you turn the thread, this disc moves up, which then opens up a gap over there for the fluid to flow through. As you turn the wheel the other way around, the threaded part will cause it to move down, which pushes this disc down and causes it to close off the opening. Good point. Let me just quickly double check something. I just want to double check because I know I changed it sometime. Okay, cool. Sorry about that. I'll upload it. I'm just making a note of it. I'll upload the updated slides on ClickUp right after the session for you. Sorry about that. Okay. So those taps are basically a variation on the ball valve, just with a more complicated ball mechanism on the inside. Maybe go check it out on the internet, as it's not super relevant for this lecture now, but it's basically got two ball valves next to each other, one for cold, one for hot. And as you move the handle, I think it's called a mixer tap. So as you move the handle, it changes the size of opening that each of the ball valves lines up with, and then that will change the amount of hot or cold water that flows through the tap. Okay, so with normal taps, the cross-sectional area is varied by means of an adjustable disc to set the size of the opening for the flow to pass through. The disc is adjusted by means of a threaded shaft with a rotating handle. Basically the same way a normal tap works. Usually on that disc there's a non-metallic part, either plastic or rubber, because the rubber seals better than metal on metal. Which is a bit of a dodgy statement because gas bottles have metal on metal, but that's because gases also don't have all kinds of foreign particles flying through them. Okay, these tabs, like you saw in your physics classes at school, have a cone-shaped member on the inside where if you turn it 90 degrees it will block the flow, and if you turn it back again it will open up the flow. So this assembly exercise is basically just that. The detailed drawings of the components used in a stop tab are shown in the following figure. Assemble the components and create the following drawings of the stop tab. A full section principal view. Remember, with assembly drawings it's actually normal to have a section view because we want to show how the stuff gets put together and where everything lies with respect to the other stuff on the inside. And then add the relevant dimensions and include a part list with appropriate part names and numbers. Just a note, the two O-rings are made of rubber and they flatten out to seal against fluid leaking out. Yeah, thanks. I will upload them right after the session. So here we have a number of components given. At the top left, we've got this circle shape. From the side, it has rounded edges, so that tells me this, and that's given as a diameter. So this is almost like a donut. This example was actually from an old semester test. Just quickly disassembling the thing. Okay, so we have these two donut shapes. The one has a 12 millimeter distance from one side to the other one is 16. Here we have a washer. It's got a diameter 8 hole through it, and the 8 hole isn't perfectly circular. It's got a flat side to it, and it's got some other protrusion on the other side. Thickness of 2.5. Here we have a nut. Just forgive the typing error there. It's supposed to be M6. 10 millimeter width, 4 millimeter thickness. Here we have the body of the valve, diameter of 40, flat at the top, flat at the bottom. It's got a cone through the middle with a diameter of 12 at the small side, angle of 97 degrees. On the right hand side, it's got a cone cut into it with an angle of 75. Big side is 16. So no, we won't expect you to make multiple orthographic drawings of a single assembly part. No. Here we have a nut. It's got an M24 by 2 thread on the inside. But if you look carefully on the right hand side of this nut, it's got a closed off portion or smaller portion. So this is a special nut. And it's got a hole drilled through it there with a diameter of 15 and a shoulder on the inside there. So the nut open, what it would look like. Okay, so that hole has a diameter of 15 millimeters according to the question. There it shows diameter 15. Okay, beneath it there is a little pipe with a cone at the end, angle of 75. The big side of that cone, however, is 17. We had a cone with a 75 up here, where the big side was 16. So it can fit in, but not all the way. So I can bring it in. And you'll notice, remember, this cone over there was 17, that one was 16. So that's why it can't go in all the way. There's going to be a little bit of a gap. No, that's not a nylock nut. It's a special kind of nut used to retain the little pipe at the end. Nylock nuts do look quite similar, but the difference in diameter between that and the threaded part isn't so severe. And also that part there is made of plastic. Okay. Then at the bottom left, our last component has a big cone to it. And it's got two of these circular grooves that are cut around the circumference. This one has a diameter of 3 millimeters for the cross section and a radius of 8. So from center to center it is 16. We've seen that somewhere. The one at the bottom is 6 from the center of the cross section to the center of the rotation of that part. So from that center to that center is 12. Diameter 3 lines up well with that component. Okay, so because it's rubber, remember now rubber is elastic, so you can stretch it over that component. If it was any other material, then we wouldn't have been able to assemble it like this. Okay, so this component now has these two rubbers around it, and in the question it actually said the two O-rings are made of rubber and they flatten out to seal against fluid leaking out. So as I squeeze this cone in somewhere, the two seals will seal. That cone is given with an angle over there of 83. So if we want to calculate that angle at the bottom there, we can take 180 minus 83 gives you 97. Hey, we've seen 97 somewhere. Diameter 12, diameter 12. So this cone can go into that cone. Okie dokie. And it can go in up to where the diameter 12s line up with each other. Okay, put the rubbers on and then drop it into place. Okay, something like that. This shaft also has a part that I forgot to dimension when I set up this test. The diameter over there. And I also forgot to dimension that thread, which was the M6, and that thickness of 2. Okay, basically that is a circular disc with the side of it cut flat. Basically like that. So somewhere else where we saw that was in this washer. So if I put the washer over the end of the shaft and I put the nut over the top of that, it will actually keep the washer in its place. Now this washer has the protrusion over there, and that protrusion is used specifically to limit the amount of rotation that this thing can undergo. So it can only rotate until that plane touches that plane. Up to there and up to there. So it's basically a mechanical method to stop the handle from spinning all the way around. Okay. Easy stuff. And this now basically shows us the assembled tap. So at the moment that hole lines up with the hole through the whole, well, entire tap. So we can see all the way through it. If I turn the handle, then I would then change the orientation of that big cone with respect to the body of the tap. I just want to quickly see. I can't momentarily just hide that inch. Oh, yeah, like that. Okay, so as I turn the handle, now I can see through it. As I turn it smaller, the gap becomes smaller and smaller. So technically water can still come in here. So the water will still come in here, flow to there, flow through that little gap into there, out the little gap on the other side, and out through the outside of the tap. If I turned this handle of the tap a little more, from this point onwards, the tap is completely closed. And if I turn it the other way, there the tap is now completely open. Okay, that's a good question. So remember this washer had that flattened part on it there. So that flattened part forces the washer to turn with the shaft. Let me just quickly fix that. Okay, so that forces, if I turn the shaft, that the washer will turn as well. Meaning the thread is not affected by the turn of the handle because everything at the bottom there, including the nut, are forced to turn together. Okay, I'll just have to add a mate for that nut because at the moment the way I set up the assembly, it's going to stand still. Okay. So that's basically what it looks like when we do the section drawing of this component. We need to show three kinds of dimensions. Overall dimension, so that's the overall length, overall width, overall height. So in this one's case, calculating the height was a bit tricky, so we gave you up to 5 millimeters either way. Then mounting dimension, we could consider this thread on the end as a mounting dimension, so that 17 long M16 thread can be a mounting dimension. And then a functional dimension, what do I need to know to be able to use this? I need to know the diameter of the hole going all the way through the middle. That tells me how big of a tap it is. I need to know the length of the handle. It tells me how strong I will have to be able to turn the handle. And I need to know what the size of the interface would be on this right-hand side there. So those would be our functional dimensions. Then I add part names, quantity, and all the balloons, description, and material. Okay, so the tap ends are hexagonal for a very good reason. The tool that you will use to tighten this, the tap or to fit the tap is a tool that's designed to grab hold of hexagonal shapes. Okay, so these are flat now, but usually you get them. A hex is basically 3 flats. Are taps scary? Are you going to be required to use SolidWorks anytime soon? Well, yes, you have a SolidWorks assignment on at the moment, due for handing in just more than 2 weeks' time. Okay, so those assemblies were pre-made. So I basically just suppressed all of the mates, moved the stuff around, and then afterwards unsuppressed the mates to bring it all back together again. So that's how I did that. Okay, why there are 2 different hatching lines in different directions. There should be more than 2 different ones. Basically, different hatching angles or spacings tell me that these are different components. So this one over here is the nut going around the outside. That one there is the body of the tap. This one is the pipe connection on the end. That hatching there is the rotary component where the handle is attached to. The washers are too small to hatch, so I colored them in. And you'll notice that small part there is also hatched differently as well.